In this video, we will be covering motion in one dimension. We'll start with distance and displacement. We'll go on to finding the velocity and acceleration, and we'll also look at a few kinematic equations. Motion in one dimension. Let's begin by describing the term kinematics. Kinematics means the study of motion while ignoring its cause. So basically we just look at what is happening and not why it is happening. So kinematics describes motion while ignoring the external agents, which is the force, that might have caused or modified the motion. So in this lecture we'll only consider motion in one dimension, that is along a straight line. So motion means a continuous change in an object's position, and we'll be using the particle model. So we'll be considering all everyday objects as point masses. So we'll ignore their dimensions, we'll consider them to be point masses having mass, but very small size. So this can be done only because the size of the object is very less as compared to the distance traveled by the object. Position. The object's position is its location with respect to a chosen reference point. So let's say in this figure we choose 0 to be a reference. So if a car moves to 30, so we say that it has moved 30, whatever the unit is, in this case it's meters, so 30 meters from 0. So in this case 0 is the reference, we call it the origin. So the position is nothing but its location with respect to a chosen reference point. So let's see what displacement means. Displacement is defined as the change in position during a time interval. It's represented by delta x, which is given as x final minus x initial. Now one must notice that displacement does not depend on the path taken by the object. It only depends on the final and initial points. So basically displacement is nothing but the shortest distance between the starting and the end point. It's different from distance. Distance is the total length of a path followed by a particle, but displacement is the shortest distance between the starting and the end point. So let's consider the tip of a clock hand. It starts from 12, goes all around the clock in a circle and comes back to 12. So in that case, the distance traveled by the tip of the hand will be 2 pi r, where r is the radius of the clock. But the displacement will be 0 because it's returning to the same position. The average velocity is the rate at which the displacement occurs. So we say that average velocity is a measure of the rate of change of displacement with respect to time. So we define V average as delta x by delta t, where delta x is the displacement, x final minus x initial, upon delta t, the time interval in which the displacement occurred. Here we are considering motion along the x-axis, so we are taking this to be Vx and delta x, and we'll only be considering single dimensional motion in this chapter. Also, when we try to represent a body's motion using a graph of position with time, we find that the slope of the graph turns out to be the average velocity. Now let's see what average speed means. Now this is different from velocity. Speed and velocity are not the same things. Speed is a scalar quantity, but velocity is a vector. Velocity has direction. We don't consider direction in speed. But both of them have the same units, which is meter per second. Now speed is defined as total distance upon total time. Now remember, velocity was total displacement upon the time interval. The speed does not have any direction and it's just expressed as a positive number. Now, instantaneous velocity. we say that the limit of the average velocity as the time interval becomes infinitely small, or as the time interval approaches zero, to be the instantaneous velocity. What this means is we define average velocity along x as delta x by delta t when this delta t becomes very small. So we say that t approaches 0 or delta t tends to 0. So the limit when delta t tends to 0, delta x upon delta t gives us the average, the instantaneous velocity. So the instantaneous velocity tells us what is happening at every point of time. The general equation for instantaneous velocity is limit delta t tends to 0 delta x by delta t, which then becomes dx upon dt, differentiation of x in terms of t with respect to t. Now acceleration is the rate of change of velocity. Now, as velocity is the rate of change of displacement, similarly acceleration is the rate of change of velocity. So we see that ax average is given as delta vx by delta t, which is again vx final minus vx initial upon tf minus ta, which is the time interval delta t. And the units for acceleration are meter per second square. In one dimension, we can use a positive or a negative sign to indicate the direction of acceleration. And just like instantaneous velocity, instantaneous acceleration is the limit of the average acceleration as delta t approaches 0. So we know that a is delta vx upon delta t, and as t approaches 0, we have the instantaneous acceleration given by dvx by dt. Now because vx is again dx by dt, we can say that ax is d2x by dt square, which is the double differentiation of the displacement in terms of time. Now let's see how acceleration is related to force. The acceleration of an object is directly proportional to the force acting on the object in the same direction. Now, if the force is in the same direction as the velocity, then the object speeds up. So we say that the acceleration is positive. But if the velocity and acceleration are in opposite directions, so the force is in the opposite direction and the velocity decreases gradually, we call this to be the case of negative acceleration or retardation. Now let's take a look at a few equations which will help us look at and study a body's motion better. The first equation is Vxf, which is the final velocity, is given as the initial velocity plus acceleration into time when the acceleration is constant. So let's look deeper into this. When acceleration is constant, the velocity increases at a uniform rate. So we say that the final velocity is given by the initial velocity. So this is the velocity when we start taking our measurements and we consider that time to be 0. So Vx final is given as initial velocity plus Ax into t, where Ax is the constant acceleration. We studied the same equation in high school as V is equal to U plus At. It's just another way of writing it. The second equation is again a case of constant acceleration. In this we say that if acceleration is constant, then the average velocity in a given time interval can be directly found as initial velocity plus final velocity divided by 2. So the average velocity is just the arithmetic mean of the initial and final velocities, but remember this applies only when the acceleration is constant. Now for constant acceleration, the final position is given as initial position plus v into t, where this is the average velocity. And we know that average velocity can be written as vxi plus vfx upon 2 in the case of constant acceleration, as we just saw in the previous slide. So I can just replace V average by this expression, half into Vxi plus Vxf. So this gives you the position of the particle in terms of time and velocities, but it doesn't give you anything about the acceleration. Now this equation gives the final position in terms of velocity and acceleration. So xf is given as xi plus vxit, the initial velocity into time, plus half ax square. Now again remember, acceleration is constant in this case, and in this formula we've studied as s is equal to ut plus half at square. Now this is just the term which tells us the initial position of the object. If we consider that to be 0, then this becomes the same equation, s is equal to ut plus half at square. So we just write this to be more concise and clear. xf final position given as xi plus vxi into t plus half axt square. Now for constant acceleration, we see that velocity final, the final velocity squared, is equal to initial velocity squared plus 2 into acceleration into the displacement xf minus xf. Now this expression gives us the final velocity in terms of acceleration and displacement. Now we should also consider the case when acceleration becomes 0. So when acceleration is 0, the rate of change of velocity is 0. So the velocity does not change. So the final velocity is equal to the initial velocity, and we can denote both by just writing Vx and eliminating f or I suffixes. And xf becomes xi plus vxt because the acceleration is 0. The third term, half at square, is eliminated.